As for today, we're going to look at the probability lecture 2 and the probability rules that are involved. Everything comes down to make a picture, make a picture, make a picture. These are the 3 rules of statistics every time. And we're going to see lots of different pictures that we look at, but for probability, there are 3: Venn diagram, tree diagram, and then a table quote picture, because a table is just abbreviated information. We saw last time, we looked at the general addition rule. All right, probability of A or B equals the probability of A plus B. That was a Venn diagram, which we called the disjoint case. Disjoint means not overlapping. And this one, probability of A or B equals the probability of A plus the probability of B. As simple as it gets. Or always means add. Now, what I talked about last time is or always means add and always means multiply, but what are you multiplying? What are you adding? The other situation we have is what's known as the overlapping case. Now, notice the formula here for the general addition rule. It still says probability of A or B equals the probability of A plus the probability of B, but you have to minus the middle because it's getting double counted. When you add the probability of A plus the probability of B, that middle piece got counted twice, which means you have to subtract it out once. And so notice, or still means add. Subtraction is just adding a negative. So it's all still being added. You just have to make sure that you know what you're adding or subtracting. So both of these cases, all right, your or means add, but what you're adding could be different. And so this is why a picture is always going to be crucial for us, because you don't just add the same things every time. You have to see what's happening in that situation. Just want to make sure that everyone good. Almost there. No problem. We got time. Okay, you're good now. All right, so what's always most helpful? Let's look at an example. So suppose that 90% of Gillette students have a cell phone, 36% have an iPod, and 30% have both a cell phone and an iPod. What is the probability that a randomly selected Gillette student has this, or this? So with everything, we always start by identifying our information. We want to write out our information in a way that is most helpful to us, and the way that is most helpful is using information. So I'm going to call cell phone C. Probability of C is 90%. Probability of iPod, I'm going to call I. And probability both cell phone and an iPod. Now, be aware the temptation I see a lot is people like to write probability of B for both. You want to keep your notation as minimal as possible. Always use the not notation, C and C not, and if you have a combination, instead of writing probability B for both cell phone and iPod, so it's much better to write this as C and I. Use a connector and limit the amount of variables that you're creating. Because all of a sudden, if you get down a problem and you have 10 different variables when you actually only needed 2, right? I see way too much confusion. All right, so I have cell phone, iPod, and cell phone and iPod. So just by the information presented, I know I'm going to create a picture that is the overlapping case. Now, all right, so I have my picture, and if you notice about these probabilities, when you add them all up, what number do we get? Not the exact number, but is it over a particular value that's important in probability?
100%.
It's over 100%. It's because stuff is being double counted. So what's better than one picture? How about two pictures? I recommend, all right, when we're doing Venn diagrams, you create two pictures. So this, I'm going to look at each piece individually, but this one is going to be things without, it's only each piece. Basically, this is the disjoint mutually exclusive overlapping case, all right? I just call this the half moon pick. The middle piece still is the same middle piece. So C and I didn't change. That's still 30%. But now I want to look, all right, at just these other half moons on the outside. And if I'm looking at only this part, getting rid of the people who have both a cell phone and an iPod, all right? In words, who are these people? These are people who have what?
Only cell phones.
Only a cell phone. All right, so you can write this as only cell phone, just cell phone, all right? Or completely using notation, C and not I. I have a cell phone and no iPod. In order to do that calculation, what do you think we do?
Subtract.
Go ahead, Mateo.
Subtract.
Yeah, subtract. 90 minus 30. Be aware the other door is always unlocked.
Oh, okay.
Yeah, so if anyone's ever late, that door always. And similarly, these would be the people with only an iPod, aka no cell phone, and an iPod, and that's 6%. And already I know these numbers look a little better because 60 plus 30 plus 6, I'm under 100%. So that's 96, which means I have 4% left over. That's the people on the outside. Now the good news is, these people on the outside is the same for both. So in words, who are these 4% of people?
Have none.
In context.
People without a cell phone.
Correct. I have neither a cell phone nor an iPod. I could also say that as I do not have a cell phone and I do not have an iPod. So either way, you want to write that out. All right, are correct. And the good news is that the outside is the same. And these numbers, all right, in the top picture, all right, they do match up because 90% plus 36% minus 30% is still that same 96. But the half moon pick really gives us like a more visual display. And again, one, right, we're all about making a picture. What's better than one picture? Two pictures. All the info is there, and I have everything pulled in out separately. I have things grouped together, all right? So very, very helpful. The big thing is statistics is not like math. Notice what I haven't even done yet. I haven't even answered the first question because all I've done is identify information and then I've made my pictures. Getting everything set up then makes your problems go very, very fast. The biggest mistake I always see is people read the problem, they highlight a couple things and then they start to go to the first problem. They go, oh, I don't know what I'm doing, right? It's because people, they rush into the problem too much and we need to set it up. Stats is all about setup. Identify what you have, write it out as thoroughly as you can, visually display it, then let's see what's being asked. All right, so what is the probability that a randomly selected student has a cell phone or an iPod? So probability cell phone or iPod. Now I could use the formula that we just found. Probability C plus probability of I minus probability C and I. And this basically uses the top picture. 0.9 plus 0.36 minus 0.30 equals 0.96. Now, if you love formulas, that's what you can do. I'm all about using the pictures and just using logic. That's why the half moon pick is so great here. It's literally that piece, and that piece. Once I have my picture, I can see it's 96%. There is no work to write out. I could just look and say it's 96%. That's from my picture. Just so you could see that in formula form though, I could also write it as probability of C and not I plus the probability of C and I plus the probability of not C and I. Which this one uses all the info from the half moon pick. And of course, we end up with the same value. Just since we're talking about it, all right, there is one more way to do this, even though we have thoroughly answered this question. C or I, right? It means it could be one or the other or both, right? And this brings up an important point that the English language has evolved. Math, as far as English translating to words, has not. Or always means including both, right? When you actually speak and you say, oh, do I want a cell phone and or an iPod, actually is how we say it in English now, to be even more specific, because or could mean one or the other or both, but it doesn't have to be, all right? English has evolved to the point where it's so confusing. Math, just so you know, when we say or, it always means one or the other or both, all right? Okay, and so along those points, because I was like, it means one or the other or both, that's a complicated way. When you have something that's really complicated, all right, from last class, what did we talk about? When something's really complicated one way, what's the way to do it the opposite? What do? What's it called? Remember? The complement, right? So I could also do this as the complement. What's the complement of one or the other? How about neither? And that, it means it's just one minus the outside, right, that we found. And of course, that is 96 as well. Okay. Probability that the randomly selected just student has neither a cell phone nor an iPod. And that one we have already answered multiple times. Probability neither a cell phone nor an iPod. 0.4 from our picture. And lastly, has a cell phone but no iPod. Probability C or not I. And also, that is from our picture as well. All right, C and no I, that's our 0.6. So this is why when you draw a really, really thorough picture, all right, that really, really thorough picture, all right, answers basically every question. And I wrote part A out like a bunch of different ways, but I could have just looked at my picture and gotten the answer there as well. The big thing is, again, like I said, how much work you show in between is up to you. All right. What you must have is the probability statement that identifies what you're looking for, and then the value, all right? Like showing the adding and subtracting, I did that just so we could see what's happening. All right. Draw a picture, draw a picture, draw a picture.
Mediocre skills will come in handy.
Yeah, like notice this picture is not to scale by any means. How do I know this is 60%?
Because it says it's 60%.
Because I said 60%. Is this 60% of this picture? No. I was like, the value indicates the area that it represents. Okay. So the other big thing we do are conditional probabilities. All right, so there are three joint ways to connect two values that we're interested in. And, or, and given. Given represented by this horizontal line. So the notation is there to help you. Again, you don't like the notation, as long as you write it out in a sentence, that's absolutely fine. The notation is there to help shortcut, all right, what you're identifying. Givens are a very, very common thing in statistics, in mathematics in general, because it is the if-then statement. If I get paid, then I get to eat, right? So the conditional is read as B given A. So it's actually read as then B if A, right? And it works like, it is read like that because B conditioned upon A, and in the formula, it is the joint probability of A and B divided by the conditional piece. And the formula is always this way. So again, let's look at an example. So we can look at men and women from a class survey and whether or not they have ever pulled an all-nighter. So I have a table, which is our second type of picture. All right, Venn diagram is our first type of picture. A table is our second type of quote picture. All right, because a table is not actually a picture, but it has a lot of information that is actually really well laid out for us. When you get a table, the very first thing you need to do is do all the totals. Now I've done that for us, but a lot of times we would only get these initial four values, or however many values there are. The very first thing you do, sum across the rows, sum across the columns, and then make sure these two values equal the overall total. This means, all right, that this 87 plus 163 makes 250, and this 114 plus 136 makes 250. There were 250 total students in this survey. So, all right, from that, then I can answer all kinds of questions. So let's start with the biggest one. What is the marginal distribution of gender? Let's break this down piece by piece. Marginal. All right, that is the margin. Where is the margin of your paper?
On the side.
The edges, absolutely. Okay, so that means the edge. All right, distribution. All right, what does distribution mean?
Like plugging things into each other.
If I distribute, and let's fundamental word again, distribute. If I was to distribute, all right, a deck of cards across the class, what does that mean?
Hand out.
Hand out, or more generally, spread out. All right, so how the edges are spread out. And the important part of that, when I say distribute, it means distribute the entirety. It has to sum to 100%. So it has to spread out the entirety of that deck of cards, all right? Otherwise, you're doing what's known as partial distribution. If I only give each of you one card, I'm still holding 48 unless I'm counting myself in. All right? It has to, the edges that sum to 100% spread out. So gender, all right? The edge of the gender category is along this total, which means I'm looking at these values. All right, there are two genders. male and female. And I have 114 males and 136 females. And here's the important part. Sums to 1. It has to be summing to 100%. So what do I do to that 114 and that 136? In order to make this a probability instead of a value, a count. Any guesses? Divide by
100,
100?
250,
How about 250? The number that was actually in the survey. So a distribution is how, all right, something sums to 100% and how it is spread out, right? So, I mean, this is about 50%, 50%, 40% males, or it's probably more like 45, 55, right? Percent. All right. What is the probability that a randomly selected student has ever pulled an all-nighter? This brings up a big point about creating notation. So notice that the categories of all-nighter are all-nighter yes and all-nighter no. Yes and no are the worst variables to identify as probability of Y, probability of like N, you know? You never want to use yes and no because it's actually not descriptive. So the much better notation to use here is, let's call this one AN, and then what's the opposite of AN?
Not an.
Not AN. So you always want to use notation that is descriptive enough. M and F, male, female, I mean, that's notation we use all the time, all right? Yes and no is often notation that is presented, but you need to make sure that you look at the general category and fix that notation. So, probability of AN, and in that case, how many students pulled an all-nighter?
87.
87. But remember, this is a probability, so out of 250. So always make sure that you total in, right, the overall probability. What is the probability that a randomly selected student is male and has pulled an all-nighter? Probability male and all-nighter. So how many students are male and have pulled an all-nighter? 36, thought I heard it. Out of 250. All right, so always make sure you are creating your probabilities, all right? Value out of value, and that's what it is every single time. All right, now, here's the adjustment. What is the probability that a randomly selected student is male, given that the student has ever pulled an all-nighter? So now we're looking at that conditional probability notation. And I know it's a conditional probability. This one straight out says given. All right, so we need to make sure we're doing our notation correctly. Remember, the given piece is second. So probability of male given all-nighter. All right, if you're going to use the notation, we have to make sure we use the notation properly. If you don't like the notation, write a sentence. All right. Every time, and again, like I said, a sentence is actually better, but writing out that whole sentence basically means you're restating the question, all right? Which is fine, okay? But that's just that much more writing you have to do. And believe we have plenty of writing in statistics. The probability notation is there to shorten your life. So using the definition from above, all right, it says the probability of B given A equals the probability of A and B divided by the given piece. All right, so let's use that definition to find male given all-nighter. So it says probability of M and AN divided by the probability of AN. And oh, look at that, male and AN. I found that right here. Probability of AN. I found that right here. Which means I have 36 divided by 250 divided by 87 out of 250, which equals 36 divided by 87. Now, here's the nice thing. Tables, I can actually shortcut that definition. Sometimes you have to use the definition, so you want to be able to use the definition. All right, but, all right, with this definition, I can actually just go directly, and I could have pulled this out of the table. Male given all-nighter. That means I'm only looking at those who pulled an all-nighter, which means these are the only people I cared about, was this column of people. And then I say, of that column, of those 87, how many of those were male? 36, which is what we ended up with, 36 out of 87. So if you have a table, you don't have to use the full definition, you just use logic and look at the table. Let's look at that again. Assuming the student is male, what is the probability that a randomly selected student has ever pulled an all-nighter? So, like I said, there's only 3 ways to connect 2 probabilities. I have some with males, some with all-nighters. And, or given. Is this an and? Is this male and all-nighters?
Yes.
Yes?
Oh,
This is saying, what's the probability of being a male and all-nighter? What word is this missing? If it was male and all-nighter.
Given?
You're saying this is a given?
No, that's the word that's missing.
Oh, it doesn't have the word given, you're correct. Right here, what's the probability that a randomly selected student is male and has pulled an all-nighter? What word does this not have? And. All right, is this or? Is this male or all-nighter? No, because what word is it missing? Or, which means there's only one option left, which is what I thought you were saying. All right, it's given. Now, does this say the word given?
No.
No. What word is kind of close to the word given?
Assuming.
Assuming. Given, all right, like the English language has evolved. I don't always say, given I get paid, then I eat. I don't know, right? We don't always talk in if-thens. We say these things subtly. Assuming I get paid, then I get to eat, right? If I get paid, then I get to eat, right? Suppose I get paid, then I will eat. So given is the most subtle connector word that we have in probability. But it basically works just like we just did. If it doesn't say and, it doesn't say or, it must be a given, right? And that's basically how you approach these problems. Because the good news, right, this is still intro stats. We're only looking at those 3. There are much more than 3 ways to connect 2 variables, right? But we are only going to investigate those 3. So this is actually saying probability given male, all right? What's probability student pulled an all-nighter? All right, remember the given piece is always second. Now, I could use the definition, but let's go back to the table and see if we can just find it that way. So given the student is male, how many males were there? How many?
114.
114 males, right? You're on the second part already. Now, of those 114, how many pulled an all-nighter? 36. And so that one, I can say 36 out of 114. Right? And that's basically, with a table, the conditionals are actually very, very easy. The biggest thing always, right, is setting up the probability statement, which is always why I encourage people before. Everyone loves to go to the number and then go back to the probability statement, which is absolutely fine. That's a good way to start, but don't forget, you need both pieces. All right, so the general multiplication rule. We saw last time that and always means multiply, and that is true, but it depends on the situation. If A and B are independent, then the probability of A and B equals the probability of A times the probability of B. Very, very simple, straightforward. However, if A and B are dependent, then the probability of A and B equals the probability of A times the probability of B given A, or the probability of B times the probability of A given B. So once again, and always means multiply, but what is being multiplied changes. And this comes to that big thing that I said, okay, we're gonna put that aside for the moment. But now we need to come back to it. Independence. It is super, super easy, all right, to assume everything is independent. But the truth is that, right, the definition of independence is one thing doesn't influence another. But the truth is most things influence other things. In the real world, most things are dependent, not independent. It's the whole concept of, right, a butterfly flaps its wings and there's a tidal wave halfway across the world. Because most things are actually influenced. Everyone thinks that, oh, and it comes to people too. Oh, I'm a snowflake. I'm the only one like me. Yes, that's true, but actually, you have a lot of similar opinions to people in your same categories. We're not actually snowflakes, we're snow. Most people, all right, are related, all right? And a classic example, all right, is gender is dependent upon political affiliation, all right? Now, there's always outliers, but the vast majority is that particular genders vote particular ways, all right? And these are all studies that are done over and over and over again. All right, so back to our definition here. Events A and B are independent when the conditional probability equals the unconditional probability, all right? And this says the same thing. A given B equals the probability of A, B given A equals the probability of B. So back to our eating example, right? If I get paid, then I eat. Is that the same as I get to eat? It might be, all right? But the whole point is, all right, is that we have to identify that within context. So let's look back to our all-nighter and gender example. Is the probability of pulling an all-nighter independent of the gender of a student? So we already found the probability of all-nighter, and we already found the probability of all-nighter given males. I turned those fractions into probabilities. So, all right, the probability of all-nighter was 35-ish%. The probability of all-nighter given male was 32%. 35%, is that equal to 32%? No, not exactly. All right, so this then also comes into another gray area. So according to the official definition, these are not equal, hence these are not independent. We have something what's known as practical independence. Because like I said, in the real world, there is no such thing as things being perfectly independent. But we do still say some things are independent, and it's because they are practically independent. If these two numbers, all right, if when compared, if when the probability of B given A is compared to the probability of B, all right, as it says in the definition right there, and the value and the values are within 4%, we say the events are practically independent. All right. There is no such thing as perfect independence. All right. It does not exist except in things like dice and coins. All right. Objects that we know do not, one outcome influences the other. But when it comes to humans, Humans are complicated. There is no such thing as this does not affect this. Everything you do affects something else, right? So we say that things are practically independent when these values are close. So back to our example here, is 35% within 4% of 32%? So are pulling an all-nighter and gender practically independent? Yes, all right, and so that's basically how we get around that. Because otherwise, literally everything would be dependent.
It does make it nice and simple.
It does what?
It makes it nice and simple.
If everything's dependent? I mean, yes, that means that no matter what is asked, it's always dependent. But, I mean, practical independence, I was like, this is statistics. The world is more gray than black and white. And so we need gray rules, right? Also, that 4% is kind of a wishy-washy value as well. Sometimes we kind of go to 5%. Sometimes we kind of go to 6%. It is not a hard and fast rule, all right? So just so you're aware of that. And that's a super good point.
Thank you.
All right, so what we talked about last time as well, independent events, all right, cannot be disjoint and vice versa. All right, it's because by definition, disjoint, once something is disjoint, you know, all right, the result of another outcome, all right? The probability, right, of getting an A in a course. That means if I have an A, I know the probability of getting a B in that course. It's 0. So this knowing this probability immediately affects that other probability. So be aware this doesn't work the other way. Overlapping events can be either independent or dependent. But basically, disjoint events are always dependent, right? But once again, in the real world, what happens more often? Most things are overlapping events, which means then they could be independent or dependent. The definition of showing two things are disjoint is very, very simple, right? You see it as soon as you draw a picture or as soon as you identify information, right? But we're all about mathematically proving things, right? So, or justifying. So everything that I do with a mathematical justification, you can do with a sentence description, which is again, the better way. The mathematical justification is just shorter to write, always. But if the probability of A and B equals 0, that means they're disjoint. When you drew the picture, you drew two separate circles. If it was not 0, that means you had overlapping events. You drew overlapping pictures. Let's look at an example, because again, everything better with an example. Suppose the probability that an American has traveled to California is 18%, to New York is 9%, and to both states is 4%. Let C equal travel to California and equal travel to New York. What's the probability that an American chosen at random has traveled to California, but not New York? And then a bunch more questions. So first things first, identify information. Probability of C. Probability of N. And probability C and N. Again, whenever possible, avoid additional notation. Use the connector words and or givens. All right. Don't add more variables. All right. We can do this whole problem with 2 variables. After we identify information, what's our next big step? What are the 3 rules?
If A and B are equal to 0, then they're disjoint. Is that what you're asking?
Nope. What are the 3 rules of statistics?
I'll picture.
Oh,
Make a picture, make a picture, make a picture. We're gonna define whether they're disjoint or overlapping, but picture, identify info, then make a picture. That's basically what we do every single time. And again, instead of one picture, 2 pictures. All right, so we always want to make our pictures as thoroughly as possible. We identify our information and then we make a picture or multiple pictures. The calculations, all right, are never difficult. And as a big note here, labeling is crucial. Don't get lazy with your labeling. The probability of travel to California is 18%. But remember that this is not the travel to California. This is the probability of traveling to California and not New York. That is, travel to only California is 14%. The biggest mistake I see is when people, they label this as C and label this as C. You don't want two things with two different numbers to have the same letter. So whether you write it as only California, just California, or California and not New York, doesn't matter as long as the labeling is different. All right, don't get late. And the other big mistake I often see is people only doing the half moon pick with really, really bad notation. They call this CBN. All right, and it's just a nut. And then problems just persist because we've got, I mean, whatever that was, A through W, all right, problems to solve. You want good pictures to go back to. Set it up, take your time in the first step. All right. And so I went through the, yes.
How did you get the values of C and not N and not C and N?
Excellent. 18%, subtract 4%. Gets me 14. 9% times 4% gets me 5%. Because these, right, this is travel to only California. So I have to cut out the people who went to both. And then, how did I get that 77%?
Did you add everything together?
Which everything? I see lots of stuff.
14 and 40.
14 plus 4 plus 5 is 23. And then from that 23, what did I do?
You subtract from the-
Oh, you just.
Subtract from?
1 minus.
Yep. 1 minus 0.23 or 100 minus 23 gets me 77. Basically, 14 plus 4 plus 5 plus 77 is 100. 100, yes. All right. That has to be 100%. Because remember, this top picture can easily, as we saw in that first example, can easily be over 100%. And that's okay because all these values are basically being double counted. All right. This picture, the half moon pick, all right, those 4 values sum exactly 100%. All right. Any other questions? All right. So, and once again, what have we yet to do? Start even part A. Set up, set up, set up. All right. What's the probability that an American chosen at random has traveled to California but not New York? So probability, California and no New York, which is also more emphasis of why I love the half moon pick. Because probability of California and not New York is it's right there. We already found it. If you have good labeling, the problems go very, very fast. All right. What's the probability that an American chosen at random has traveled to either California or New York? Oh, And this actually brings, let's go back for this. So notice that this one says but, this actually didn't say and. Right? But is just a fancy way of saying and, alright? In this one, I know that I'm writing a probability with an or because what does it say? Or, alright? Also, when I get down to C, probability America chosen at random has not traveled to either state. That's an or as well. Either is another fancy way of saying or, okay? So, all these notations, all right, even though the words slightly change, they're all just various ways of saying and, or given every time. All right, so what is the probability of C or N? What is it?
Or wait, no.
That's C and N. So travel to California or New York means travel to California or New York or both.
I do.
What is it? Close. One or the other or both.
Oh.
Which means it's all three. All right. And again, this is the transition between what we say in statistics / mathematics and English. You're right. In English, when we say or, it's actually ambiguous. They could mean one or the other, or they could mean one or the other or both. But in math, we always mean one or the other or both. We don't have to say and or. So hence 23%. All right, and we already saw part C said neither. Has not traveled to either state, aka neither. And that one, we actually already found that's the outsides. All right, D. Suppose that an American has traveled to California. What is the probability that an American has also traveled to New York? All right, so what kind of problem is this?
Given.
It's a given. What's the word, the subtle word for given? Suppose. All right, and the easy way to do that is replace whatever word you think might be given with given. Given that an American has traveled to California, what is the probability the American has also traveled to New York? It's a given California, right? Yeah. So probability, given California, traveled to New York. All right, so this one is not a table. We have to use the definition. All right, which also brings up an important point. This definition, where did it go? This highlights star and asterisk this because this goes basically at the top of your cheat sheet. All right, we don't have actually that many formulas. All right, in statistics. Most of the time, we're going to use logic. All right, we use logic and pictures, all right, to do what we're looking for. There's only a few formulas, all right, that you actually can't shortcut your way around. And we even saw with a table, I can shortcut my way around this formula, but not always. All right, so the definition, probability N and C divided by the probability of C. And N and C, I have right there is 4%. And what is the probability of C?
18.
What is it?
18.
18, good. This is also what I was talking about with good labeling. All right, this one's using the top pick. If I see bad labeling here, if you called this C as well, all of a sudden people are using the only California when it's not. All right, so very important to make sure we have a good picture. 18, that's 2/9, which is 22. All right. are travel to California and New York disjoint events, and then the next one are travel to California and New York independent events. These are the two big questions, all right? And these are the two big questions that guarantee on the first quiz and likely to come back on the midterm. Like I said, are two things related? Any two things being related is the biggest question we ask in science, right? Does this relate to this? That's always what we're interested in. All right, so that's something that's going to keep coming back over and over. So one more time, let's do the definition. So the definition of disjoint is pretty straightforward. If the probability of A and B equals 0, then A and B are disjoint. So basically, all we have to do is put that into context. Instead of A and B, what do I have?
C and N.
C and N. And this is basically just asking for a comparison. Is the probability of C and N equal to 0? So what is the probability of C and N?
4%.
4%. Is 4% equal to 0%? No. Disjoint is not like independent where we have something called practically disjoint. That does not exist. So this is a definition. The probability could be 0.00001, and that is still not equal to 0. All right, so 4% is not equal, right? So values are different. Hence, travel to California and New York are overlapping events. All right, and I always get asked, oh man, do we have to write that whole sentence? That whole sentence? We're talking like 10 words here, okay?
That's a lot. I was gonna ask that, honestly.
And additionally, here's the other thing. Yeah, because, all right, this is statistics. This is not mathematics.
You need to use this.
They need to be specific, detailed, thorough, all right? The biggest thing is that statistics, it is the words that make the context, all right? This is shorthand. And a lot of times you could write this out in a sentence too, right? I was like, oh, the probability of travel to California and New York, right, is 4%. That is not 0. I can also see that in my overlapping picture, right? Hence, travel to California and New York are overlapping events, all right? So that's the big thing. Everything we do has to be about context. You have to put it into context of what you're actually looking for, all right? We will occasionally have problems like we just did parts A through D, whatever it was, where, oh, probability equals a number, probability equals a number. But a lot of what we do is proving concepts, all right? And that's what separates statistics from mathematics. All right, I don't even know what letter I'm on, E, F. All right, definition. Independent. If the probability of A given B equals the probability of A, then A and B are independent events. So once again, all right, take the definition and put it into context of whatever you're dealing with. Again, instead of A and B, we have C and N. Now, this works. Which one I call A, which one I call B, can work either way. A can be N, A could be C, doesn't matter. the best thing to do is look, did we already find a conditional?
Yeah.
Yeah, so why not use this one? I could recalculate and do C given N, but I already found N given C. All right, so using the definition, if I'm gonna do probability of N given C, I compare that to which one? To what? N or C, those are the options.
N,
Why is it N?
because it's your,
Because N became A, right? B became C, so I have to keep that consistent. Hence, that has to be N as well. Now, this does bring up a big point, and people do this all the time. It does matter. You cannot compare a conditional to the conditioned piece, right? Always think back to some, like the and I just, the if I get paid, then I eat this plus one, right? If I get paid, then I eat. Do I compare that to if I get paid? That, it doesn't make any sense, right? You have to drop the conditioned piece, and if these are still the same, then they're independent. All right, so it's a comparison. Probability of N given C was 22. Probability of N is
9%.
9. Again, always make sure, this is why good labeling, right? I'm grabbing this value. And notice, with these problems, are we using both these pictures?
Yeah.
Yeah. Should you always make both pictures? Yeah. I was like, don't be lazy. I just see it way too much. That I see some half-drawn, half-moon pick, and then a nightmare. All right? Save yourself the hassle. Take your time in the beginning, and it just goes so much better. All right, is 22% equal to 9%? No. Are they within 4%?
No.
Are they within 5? Okay, and 6 is like the farthest we really get. So, all right, they're not even kind of close.
So if it was to be close, then you would say they were independent.
Right, and so, and that's why I kind of write this part. I say the values are different, because it's kind of what your definition is. 4 to 6% is kind of the range. So someone could say, let's call the values 22 and 27. And they could say, the values are different, I'm dependent. Or you could also say, the values are close, they're within 5%, they're the same. So it's what's your definition of close, all right? So there's some gray here for sure. And that's why you have to be specific. You have to explain it, what it is to you. Now, no one says that 20 and 30 are close, all right? So there has to be a limit on what you consider close, right? And that's the thing. All right, so values are different, hence travel to California and New York are dependent events. All right, and this one is pretty easy. Different, dependent. All right, DD. Values different, they're dependent. Values are the same, independent. That one doesn't match up. I don't know, but is there a word for equal that starts with an I?
There might.
I'm sure there is. Yes, you are correct. All right, so our third picture, tree diagrams. All right, tree diagrams are all about showing things, all right, with lots of conditionals. All right, we're going to talk about this one next time. But this all comes down to, all right, in the problem, you have tons and tons of conditionals. Venn diagrams are all about when you have lots of ands and ors. Tables are obviously when you are presented a table, and tree diagrams are all about when you have lots of conditionals. Those are the only three pictures we have for all of probability. All right. So there is a wonderful activity if you want to take a look at it, probability activity 2. All right. Otherwise, this has been a wonderful first week in statistics. And I was like, you could have yourself a good weekend or hang around and do problems. Happy to help. Up to you.
The tree diagram, like,
Just basically looks like a bunch of branches. Branches and a branch. I mean, you know, like when you draw a family tree like that.